The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
What I'm going to talk about is some of the studies that we have done with limestone bearing systems, and especially we've done a lot of work on limestone bearing systems on a variety of different aspects, from fundamental chemistry of what forms to how does reaction happens, tagging on some of the stuff that Jason talked about a few minutes ago, and also on ionic transport. I'll quickly go through a few of those just to lay the ground for what I'm trying to explain here. So, what we are going to look at is the fundamental effects of what limestone does in cementitious systems. We have cement manufacturers making underground limestone. You have limestone producers being able to give you limestone so that you can blend in cement systems. Like Jason said, when you intergrind it, you're going to have extremely small size of limestone. If you blend it, you can control the particle sizes. So there are a variety of opportunities that are available for a concrete producer, for an infrastructure owner, whoever it is, to look at what different properties they can get. The important thing that I want to bring about in this study is to get into this idea that limestone by itself might not do all that you want to do in a concrete system, because you're loading it with a lot of carbonates. When you're intergrinding with 10 to 12% of carbonates, you have a lot of carbonates sitting in the system without doing much. Now, for a cement producer, it might not be a bad deal because he has limestone right with him as a free source. He can intergrind it. It's a nice, cheap, easy filler for him. That is perfectly fine. But really, it might not do what you actually want it to do in terms of concrete properties. So, our focus has always been synergizing limestone, the carbonates, with something that it can play around with in giving you the properties that you want eventually. So we look at the relative effects of clinker fraction reduction. So basically you reduce clinker factor by 20, 30, 40, 50%. So basically taking out 50% of cement, still being able to get 75, 80, 90% of concrete properties that you would otherwise get. And that is what at the end of the day you want from a performance-based specification point of view. It's not how much you put of what you put in, it is what performance you're getting in your concrete. So how do you proportion for that? So we'll look at some chemistry aspects, and then if the audience has the mood to listen and we have the time, I'll show you a modeling strategy that can look at how do we do mathematically predict what is happening when you have chlorides in the system, for example. Okay, so very similar ideas. If you have very small limestone particles, you have a lot of surface area for reactions. You will see that with limestone, you will see that heat of hydration goes up. The same idea, the rate curve that Jason showed, the same idea. You will see that you will have a higher amount of heat. Now, where is that coming from? You have a higher rate of reaction because all these very small limestone particles are making your cement hydrate better, because these are also for cement reaction products to nucleate. So you get more surfaces, you get more walls for people to lean on, more hydration products lean onto the walls, and are very happy with that. So that's what is happening with this higher rate of reaction. Now, calcium carbonate can react with C3A to form carbonate AFM phases, the sulfate AFM, the monosulfur aluminates that we talk about with gypsum. The very similar idea, you have now excess carbonate, you can have carbonate AFM phases. This is a fairly well understood pathway of what limestone does in a certain range. It does not happen for the entire amount of limestone you put in, but for some part, this indeed happens. Where you have in gypsum, you have sulfates, so you basically are converting the sulfate AFMs to carbonate AFMs. So basically, you're getting your monosulfur aluminates to change to monocarbo aluminates. That balance, that carbonate sulfate balance now becomes key. So basically what it effectively means is you can't have the same cement with the same gypsum content doing exactly the same thing if you replace 10 or 15% of that cement with limestone. So now that becomes another balancing story. Now this can result in improved pore filling and strength enhancements, but very low amount of calcium carbonates are reactive. If you look at it, you can see that at a certain reaction level, if you look at strength, you have some increase in strength, but increasing that carbonate addition level beyond, typically that number is about 3%. If you're adding only carbonates, Anything more than 3%, you really don't have enough of cement that you took out of doing anything with the presence of limestone that you effectively have reduced strength and increasing porosity, which you don't want. I'll show you a couple of things, a little crowded slide with graphs here, but I'll explain what it is. So if I have the OPC factor 1, meaning straight cement, and if I go up to a 50% replacement with different materials, forget about all of that. I'll just talk about metakaolin just because it has a lot of aluminates. I want to show what happens with carbonates and aluminates, because we said carbonate AFM, right? Carbonate aluminate systems. So metakaolin has a lot of aluminates, very reactive aluminate. If you replace, for example, it's right here, if you have got 42% of cement that is replaced with a combination of metakaolin and limestone, your strength reduction is only of the order of 20%. So you're essentially saying that you can have a large reduction in clinker factor with strengths that are acceptable if you proportion properly. Now this shows a little bit more of chemistry of what happens here. So this is a derivative thermogravimetric analysis trace taking all the way to 1000 degrees Celsius. Jason showed one of these two, the same idea. So you have your calcium hydroxide. So here's one point again, it's a nice segue that I'm presenting after him than before. So I can take a lot of stuff from what he said already. So he showed a lot of details on what calcium hydroxide is happening. He eventually showed you, if you remember, that if you add only limestone, you have excess calcium hydroxide in the system, right? Every other pozzolanic material, you have calcium hydroxide consumption. Limestone alone was negative in that chart. The exact same idea we're showing here, but in a slightly different way. This is glass half full story now. Okay? So you have calcium hydroxide in the system. Because of cement hydration, your metakaolin or any of those pozzolanic materials will eat up your calcium hydroxide, but in the process of formation of this carboaluminate, the monocarboaluminate case, so this is with just OPC and metakaolin, look at the amount of calcium hydroxides when I replace with 15% of metakaolin. But when I have 15% of metakaolin, 30% of limestone, look at that calcium hydroxide content. This was here. This is here, the scales are the same. So now you see suddenly your calcium hydroxide dropping in the increased amounts of limestone. If I had limestone alone, what Jason showed would be exactly what happens. Now you have metakaolin or a high aluminous material along with limestone, you're consuming a lot of calcium hydroxide because that calcium hydroxide is going towards the formation of this monocarboaluminate and hemicarboaluminate. So this is a phase balance that happens in the system where sulfate AFM is replaced by carbonate AFM, calcium hydroxide goes to the consumption. Now this is double benefit for anybody who wants to reduce calcium hydroxide in concrete. You put in a lot of pozzolanic material, silica fume, metakaolin, all of that, suddenly with a little more fine limestone, you're getting double benefits. So that is the exact chemistry that goes on behind, and if we can tailor that chemistry, now the process of proportioning for a desired performance becomes much easier rather than just putting in a material. Again, some more simple graphs to show the whole idea. If I just have plain limestone replacing cement, that's how my strength will go. If I have an aluminous source, my strength is much more stable. This is at very early ages, 1 days, what different limestone particle sizes you use. So very fine limestone, you have a good effect. Coarser limestone, you really don't have that much of an effect. The same idea now. If I have to get all these better properties, if I'm saying that monocarbonates or hemicarbonates are formed at the expense of the sulfate AFM in reaction with calcium hydroxide, then my carbonates also should be consumed, right? The limestone that I add should be consumed. These are plain systems, no fly ash or metakaolin, just fly ash. This is a combination of metakaolin and fly ash with limestone systems. You will see that your carbonate contents are reduced after 1 day and 28 days. So compared to, this is a coarse limestone, so it doesn't do much, but finer limestones do a good job of carbonate production. So basically your carbonate is consumed. Now you're showing that your limestone that you're putting in is not just a filler. It did not have the potential to act as a reactive material if you put it alone. Now you're tailoring the chemistry, you're forcing it to react, and mono and hemicarbonates are not bad things in concrete. It doesn't do anything, it just fills a pores. These are actually denser products than calcium hydroxide that it replaces. Your concrete is actually going to get stronger and much more durable. So that is the first part of the chemistry with aluminates. Now, going on to slag, you will pretty much see the same story, but slag is even better because slag is cementitious too, not just pozzolanic. So slag does not rely on the calcium hydroxide alone to do its own thing. So slag is more cementitious too. So now if you look at this graph, I've reduced the clinker factor from 1 to 0.5, which means between limestone and slag, I have 50% replacement at 28 days. I have not lost any strength. There's about 20% limestone and 30% slag effectively. So now, that's the same thing. Slag also has aluminates. The alumina reaction from slag also helps it with added cementitious reaction. Again, a picture just to show what Jason said. If you intergrind all the green are the limestone particles. If you intergrind cement with limestone, the blue are the slag. If you intergrind cement with limestone, your limestone particles will look like that. If you blend, your limestone particles will look like that. Again, you can have size adjustment as much as you want. And I'll show you one more picture of beneficial synergy. This is on fracture toughness. So if I take a notched beam and load it and take it to fracture, the toughness, if you actually see here, blended mixes with metakaolin or fly ash are much higher than the plain OPC at 10% replacement level. Even at a total 35% replacement level, you have not very bad properties. Similarly, crack opening displacement, these are actually the strains that the material will see for. Basically, so if you're looking at crack propagation under load, how does a crack propagate? You are having now, because of the aluminate and limestone synergy, you are now having a matrix that is much more resistant to crack propagation. Right? So this is the evidence. You see a very focused crack propagation zone, very high strain zone where the crack will propagate through. You have a very diffused strain zone where energy is dissipated around so that it doesn't go that fast. And if you actually look at the width of the zone, you can see here again, the ternary blends have much higher width of the zone, implying energy dissipation. Coming into chloride transport. Chloride transport, like all of you know, is one of the major durability problems. Chlorides come in and start corroding the steel. We use accelerated test methods. We don't have time to pond a slab for 2 years and find out what happens to the steel. So all specification purposes uses a standard rapid chloride permeability test, which in fact is a pretty bad test for all practical purposes. It really doesn't measure what you want. It actually gives you a very happy number to play with. But it's a lot of confounding effects in chloride RCPT test which needs to be considered. But we will show a few different things. So if you are subjecting your concrete to an accelerated test where I have a chloride saturated solution on one side and a chloride deficient solution on the other side, I put an electric current to make chlorides go through, we always thought that chlorides were the only things that were going. But your concrete pore solution doesn't have chlorides alone. It has a lot of other things, other ions that are very happy to move under electrical potential. So anytime you do a rapid test in the lab, and say this is chloride permeability, what you are having is a bunch of other permeabilities too. It is not just chlorides, it is the hydroxides and the sodium and potassium especially, which are very active and can move pretty quickly. And if you're measuring resistivity tests, we do a lot of resistivity tests these days, which are indicators of permeability, indicators of durability. Anytime when you do a resistivity test in a saturated solution full of hydroxide ions, you're pretty much picking up the hydroxide ion effect predominantly. So that is something to be considered rather than just looking at those numbers. I'll show you a few ways to tackle that too. So here are the different mixes that we did. So a few mixes with 20% replacement of cement by limestone and fly ash or metakaolin, and then a few 35% replacement. So what we did in all these mixes is actually balance the blending of the cement and limestone with 3 and 10 micron medium sized limestone so that the OPC and the blend has a similar particle size distribution. So you take out the effects of particle size. Your size distribution is very similar in both those cases. So if you look at RCPT, again, this is not a very good experiment, but still for specification purpose, if people are still looking at it, you can see that limestone alone at 28 days, really 20 and 35%, okay, so not the 5% that we normally do, very high amounts, really doesn't do much. Your chloride permeability is much higher, which is not good. But if you bring in ternary mixes with fly ash, ternary mixes with metakaolin, you suddenly have, so 25% limestone, 10% metakaolin, look at where it's about half of the chloride permeability. This value is pretty much what you get when you have silica field, close to that. So again, you're using 25% of limestone in this mix. Same reason which I told earlier, the sulfate AFM being replaced by carbonate AFM and a lot of pozzolanic reaction products being formed. If you look at non-steady state migration, which is actually a much better transport test, much better transport test than RCPT. RCPT takes 6 hours, this takes 24 hours typically. But it's a much better transport test because you're not pushing in the ions at a 60 volt voltage. 60 volts for 6 hours creates a lot of heat. You have Joule heating effects too. This you typically do at 30 volts or lower, which means the heating effects are much more reduced. The ionic transport is much more under equilibrium rather than very highly forced conditions. You have a 20% replacement of cement system here, 35% replacement total. And if you look at it here, with 20% replacement, limestone, metakaolin, very low value of diffusion coefficient, even at 35%, it's much better than OPC. So again, you're seeing much more beneficial effects of the combination transport, again, fundamentally attributable to the same chemistry that I told you earlier. Now, if I really want to quantify, how do I quantify, and if I really want to use this mix, RCPD is not going to be a good parameter because the moment you have different types of ions in the system, you're actually measuring completely different things. So is there a way that I can actually measure or characterize the pore structure so that I can have much better indicators of how the transport goes on? So if you do a conductivity test, this is from AC impedance test, you can do it with DC also. But if I find the effective conductivity of the concrete, like the resistivity test, inverse of resistivity, that's a function of the conductivity of the pore solution and some parameter of the microstructure. This is a porosity, that's the connectivity of the pores. So if I take that parameter together, I can have very good correlations with how deep my ions penetrate. Penetration depth versus pore structure factor, very good correlation. Again saying that you can have a simple electrical test to find what the pore structure is and relate that pretty well to how deep the chloride ions go through. I have a couple of other things on pore structure and blended mixes. This is just to give you the idea that we have always focused on porosity when we talk about concretes. Like we say, reduce the porosity, reduce the porosity, reduce the porosity. It's been there. But while we reduce the porosity, you automatically infer that porosity reduction will result in a concomitant reduction of sizes in pores also. That was our assumption. It need not happen all the time. You can have pore volume reduction without really pore size reduction of large magnitude. So here what I want to show you is that it is the pore sizes that are important in transport. So measuring a total overall porosity might not give you the actual picture when you're looking at transport, not just for limestone concretes, but for pretty much any concretes. So if you look at limestone plus fly ash or limestone plus metakaolin, your porosities, total porosities are not really changed. What metakaolin is actually doing are very high alumina. Fly ash also has aluminas but lower amounts. What very high alumina systems are doing is to reduce your pore sizes dramatically. And this pore size reduction is what causes reduction in transport. Now, this is a bunch of stuff. This is purely academic interest about 5-6 years ago, but 6-7 years ago. I was always baffled by this idea that everybody takes pore size reduction to be understood when they say porosity reduction. And I wanted to show that's not the case. So we actually did a bunch of different tests with mixtures containing fly ash and mixtures containing silica fume, where you can actually know that silica fume mixtures have much lower transport properties at the same porosity. So I played around with the water cement ratio to actually get the same porosities, but if you look at the pore connectivity, silica fume mixes are much lower compared to the plain and fly ash mixes. And that is translated here when you look at pore sizes versus porosity. Silica fume has smaller pore sizes for the same porosity. So both these pictures together, you can show that actually it is the pore sizes that reduce the transport, not the porosity per se. Again, it's all within range, but we should always look for, so here is what I always say, pore size refinement is more important than porosity refinement, but if you can get porosity refinement with concomitant pore size refinement, that's fine because porosity refinement is easy to measure. You can quickly measure how reduced your porosity is. That's quick illustration for the fact that metakaolin mixtures with limestone have lower transport properties that you saw in the previous slides to explain these kinds of behavior. In summary, binary blends containing limestone had showed higher RCP and migration values than the OPC system, while ternary blends have much lower values. So we've explained the beneficial synergy of limestone and metakaolin, basically from the formation of mono and hemicarboaluminates and the consumption of calcium hydroxide to form the hemicarboaluminates at the expense of sulfate AFM. Pore structure factor demonstrated as a strong correlation with the penetration depth of chloride ions, and pore structure factor can be used to compare the transport performance of limestone blends. I think I can stop here. I have a little more stuff on the models, but I think I'll skip that. This is good enough for the idea that I wanted to present. Thank you.